I'm going to try to explain why it's important to try to appreciate the significance of some of the very large numbers that appear so often in scientific studies. The large numbers I'm going to generate are based on how many breaths of air that could fit into some very large volumes. And then I'm going to compare these big numbers to a physical parameter, which is also a very big number, and then end up with an application which I think might be of interest even to those who are not particularly interested in scientific studies. The breath of air is about half of a liter, and that's how much air fits in one of these little plastic bags that I have here. The volumes that I'll use, the first one is going to be a symphony hall whose dimensions were easily available. So that symphony hall, and I'm going to present this on a series of slides. I'll go over it in the first one in most detail. So the symphony hall was 75 feet wide, 125 feet long, and the ceiling was 61 feet high. So if you multiply those three numbers together, you get 570,000 cubic feet, which is the volume of that symphony hall. Now we want to convert that to breaths of air. And so you have to get some conversion factors. Most of these, this conversion factor, for example, is in pretty much any high school textbook on science or chemistry that you might find, and usually in an appendix. And the conversion factors that there are 28 liters is the same as 1 cubic foot. And so if you multiply that 570,000 cubic feet times that ratio, 28 liters to 1 cubic foot, you get the number of liters of air in that symphony hall. And then we want to get breaths of air, so there are 2 breaths, we decided, in each 1 liter. And therefore, that multiply by that factor, and you end up with how many breaths of air there were in the symphony hall, and it's about 32 million. Now, 32 million is a pretty big number, but it's still something that you could conceive of. And just as an example of how big it is, if you could fill 5 of these bags of air every minute and seal them off like this, tie them off, and place them somewhere in the symphony hall, and you took this on as a full-time job, working 40 hours a week and 50 weeks a year, it would take you 50 years in order to fill up that symphony hall with these little bags, or in other words, with all the breaths of air that will fit in that symphony hall. So that's a big number, but it's way smaller than the physical parameter that I wanted to compare it to. And so we got to get a bigger volume. And next I took, well, what about if we take the whole city where that symphony hall is located, and take all the air above that city, above the roads and the parks and the buildings and everything. And instead of going at the top of the building, we go at the top of the Earth's atmosphere. The Earth's atmosphere doesn't really have a very sharply defined top to it, because the air gets thinner and thinner as you go up higher and higher altitudes. But to talk about a breath of air, we want to compress that air at high altitudes into about the same density as it would be at sea level in order to take a breath of it. And if you compressed all the air in the Earth's atmosphere above that city so that the density was uniform, it didn't get thinner and thinner as you go up higher, but it would stay the same as it is at sea level, then the atmosphere would have a sharp top at about 5 miles high. So I rather arbitrarily picked a city that's 5 miles in the north-south direction, 5 miles in the east-west direction, and the atmosphere being 5 miles high. So it's a cube of air, 5 miles by 5 miles by 5 miles. And that's shown in the second slide. I did an intermediate step of finding out how many of those symphony halls worth of air would fit into that, would be required to fill up that one big cube of air above the city. And it turned out also to be about 32 million by just chance. So 32 million of these little bags of air to fill one symphony hall. You have to repeat that 30 million times to hold all the air above the city, and that's a really big number. It's 1 times 10 to the 15th bags of air, which is, or breaths of air, which is 1 with 15 zeros after it. But that's still smaller than this particular parameter that I wanted to compare it to. So we need a still bigger volume, and for that I took the whole atmosphere of the Earth. So that's done on this third slide. The first factor in this slide is 4 pi times the radius of the Earth squared, and that is the surface area of the Earth. And so it's actually 4 pi times the radius squared, if you've taken a geometry course, is the surface of a sphere. And we said that the atmosphere, when you compress it so that you can take breaths of air all throughout it, the atmosphere is 5 miles high. So if you multiply that surface area times 5 miles high, you get the total volume of the atmosphere of the Earth. And again, I converted this first into how many times bigger than the city worth of air it was. It was about 8 million cities worth of air. Or in terms of breaths of air, it is 8 times 10 to the 21st breaths of air in for the entire Earth's atmosphere. So we're going to keep that number, 8 times 10 to the 21st. That's 8 with 21 zeros after it, breaths of air in the entire atmosphere of the Earth. And look now at that physical parameter that I mentioned before. That's Avogadro's number. It's 6 times 10 to the 23rd, and it's the number of molecules there are in 1 mole. So we've got to see, first of all, what the atmosphere is, and second, what 1 mole is. Well, the atmosphere is about 80% nitrogen molecules and about 20% oxygen. And since it's mostly nitrogen, I'm going to assume it's all nitrogen for a while right now. So what 1 mole is you have to look up nitrogen atoms and see something properties of them and find out that they contain 7 neutrons and 7 protons for every nitrogen atom. And so the neutrons and the protons are roughly equal weights, and they are the massive part of any atom. And so that atom has 14 of these units of weight for each atom. And in the atmosphere, the molecules of nitrogen are 2 atoms that are very tightly stuck together, or bound, and therefore 1 mole of nitrogen gas is that molecular number expressed in grams. In other words, 1 mole of nitrogen gas is 28 grams of nitrogen gas. So we convert that into how many breaths of air that would be, and it turned out to be 43 breaths of air for every mole. And therefore, this 6 times 10 to the 23rd number is a number of molecules in 43 breaths of air, or in other words, 14 times 10 to the 21st molecules are in each breath of air. So that's only 2 numbers we're going to be using, the size of the Earth's atmosphere and how much there is in 1 breath of air. So it turned out, therefore, that's going to be summarized in this last slide. So there are actually more molecules of air in this one little bag than there are breaths of air in the entire atmosphere of the Earth. There are 14 times 10 to the 21st molecules in this bag. There's 8 times 10 to the 21st breaths of air in the entire atmosphere of the Earth. So the application will need one other little piece of information about the Earth's atmosphere, and that is that it stays pretty stable for hundreds of millions of years, or it has stayed pretty stable. The oxygen you're familiar with probably. It gets recycled relatively quickly because animals or humans use up oxygen when they're breathing, and that breath then your body converts oxygen to other compounds and gets energy from doing that. And also, if you burn things, it converts the oxygen to energy and produces carbon dioxide. And then the plants and the trees take up that carbon dioxide and they regenerate oxygen. So there's a cycling time for oxygen. Well, the same thing happens with nitrogen, except the fact that nitrogen is very inert compared to oxygen. And so it takes a huge amount of time to use up nitrogen. In fact, your body uses essentially none of it. You breathe in nitrogen atoms and you exhale the same nitrogen atoms as next breath. So it's not your people or animals that use up nitrogen. It's mostly microbes or bacteria in the earth, soil, and in the oceans. But they are very, very slow at using up nitrogen. And it gets reconstituted by other microbes in the soil and in the ocean. But that reconstitution time in nature takes several tens of millions of years. And now that we have people using more nitrogen, say for agricultural purposes, we're actually using up nitrogen faster than that. But even if there were people around for many millions of years, it would have taken about 10 million years for us to use up the nitrogen and have to have it reconstituted if it was going to stay, the atmosphere is supposed to stay the same. So in other words, nitrogen that's in the air has been around for a long, long time, longer than there have been people, way longer. So let's go back to the symphony hall then that I started with. Say you're sitting in that symphony hall and listening to a symphony that Beethoven composed. Well, he lived about 200 years ago, and he was breathing oxygen, breathing air, when he was composing his symphony. And so the molecules that were in Beethoven's lungs 200 years ago when he was doing this composition have now spread out over all the Earth's atmosphere. And as a result of the fact that there are more molecules in one bag of air than there are breaths of air in the entire atmosphere of the Earth, that means that there are one or two molecules from each breath of air that Beethoven took while he was composing that symphony, which are in every breath of air that you are inhaling now. In other words, thousands of molecules in every breath of air that you now inhale were inside Beethoven's lungs when he was composing that symphony. So in some rather abstract sense, Beethoven is still breathing on you, even though he's been dead for 200 years. He's breathing on you while you're listening to a symphony. In fact, he is breathing on you even when you're not listening to a symphony. It's in all the air that we breathe. But you can go back way beyond that, too, as far back as recorded history. For example, if you were sitting in a church instead of the symphony hall and listening to a sermon about Jesus, some piece of Jesus' life, well, Jesus was breathing air all the time he lived, even when he was a baby in the manger or all through his life. So any little part of his life you were talking about in this sermon, that there are thousands of molecules in every breath of air you take that were in Jesus' lungs 2,000 years ago that are now in your lungs when you're listening to the sermon, or in fact, if you're not listening, anytime. So it's sort of an interesting concept to think about, that there's this physical connection between people who are alive now, breathing, and people who were alive hundreds or even thousands of years ago. And the whole reason for this is that you would think that, oh, gee, 1,000 molecules, that's so many. How could there be that many molecules from 200 or 2,000 years ago in my lungs? Well, it's because this one bag has 14 times 10 to the 21st, 14 followed by 21 zeros. That's the number of molecules in this bag. And compared to that, 1,000 is a tiny little fraction of it. And so you have to really understand something about these huge numbers to appreciate a lot of different physical things that happen.